Welcome back to the DemystifySci podcast. I'm Anastasia.
I'm Shiloh.
This is the podcast where we explore the theories that we believe are going to change the world. To that end, you have probably heard that we are organizing a conference in Portugal for this summer about the end of the Big Bang. We've talked to a lot of astrophysicists and cosmologists that have given us a very compelling reason to believe that the theory of the Big Bang is not long for this world. So we're bringing together philosophers, observationists, theorists, critics, mainstreamers this summer in Sesimbra, Portugal, in order to get everybody into a room together to create a better map for what the future of cosmology is going to look like. To that end, we're organizing conversations with some of the speakers that are going to be at the conference in the weeks leading up to the event so that we can really lay out what it is that we plan to do there.
To that end, we have André Koch Torres Assis from the University of Campinas in Brazil. And André does a fantastic job all throughout his work, all throughout his career, of really diving into the missing history of physics and trying to understand what was happening below the surface with these mega narratives that were handed down in the textbooks. So we all know the two main pillars of the Big Bang are the cosmic redshift and the cosmic microwave background radiation. And so we're going into the stories beneath the surface that led up to those pronouncements as definitive proof of the Big Bang, because there was a lot happening that isn't obvious if you can't read the original writing for the most part. André's done an incredible job of making available translations of original writing all throughout the history of physics, and he's bringing together a lot of behind-the-scenes information as to what people were thinking before they actually turned their telescope to the sky and saw this thing that was called the cosmic microwave background radiation, because it wasn't as simple as they predicted it and found it.
And if this is a conversation that interests you, I hope that you will seriously consider meeting us this summer in Sesimbra, Portugal. Tickets for Beyond the Big Bang are available right here. In the meantime, if you want to just kind of check out a little bit more of what we do, you should come over to patreon.com/DemystifySci, and in return for your support of just a few dollars a month, you get to join our incredible patron chat that meets weekly. I think this week we are trying to figure out what the optimal amount of censorship is. For whatever reason, this is a fairly frequent discussion that comes up, but it's like, how do you build an online community? How do you build a huge community of people and then deal with the fact that some people are going to say stuff that you don't like? We have a bunch of different perspectives represented, and so we're kind of knee-deep in trying to figure that out at the patron chats. We're also going to start posting exclusive content to the Patreon, where Shiloh and I are going to debrief about episodes that we have recorded and then post those as extra episodes that you'll only get at the Patreon. If you don't have any cash to spare, that's totally fine. I understand. You can support us by liking, subscribing, leaving a comment, telling a friend, leaving a review at any of the podcast stores, and we will be absolutely eternally grateful, because without your support, without word of mouth, this podcast cannot grow. And so it is just as valuable to us as anything else that you can do. And so for now, I would say enjoy the conversation with Dr. André Koch Torres Assis about the history of how the Big Bang came to be the only theory in town.
Oh, hold on. Before we go, I wanted to mention that we have finally launched our new series at the podcast called Paradigm Drift. We had our first taping of the game show. It was incredible. And thank you so much to everybody who participated. But if you have a theory of how something works in the universe that you have been dying to share with the world, consider putting together a very abstract version of that theory and sharing it with us on Paradigm Drift Live. The next taping is going to be March 25th. It's at 6:30 Pacific. You basically get a minute to present that idea, and then Anastasia, myself, and our guest panelist will interview you about the idea, about who you are, where you came up with it, and all of that. So check it out. We'll put a link for it up here. It's also in the description, and I hope to see you at Paradigm Drift.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
I think it's just going to be wonderful to bring all of you guys together, and I hope that what happens in the in-between spaces between all of the events, I hope that there's much growth and friendships are made between all of the presenters as well, because we have the afternoons free for this conference. And so most conferences probably have talks all through the day, but we wanted to make sure there was space for you guys to actually interact outside of the formal setting.
Yes, I think that will be excellent, this meeting in Portugal in June. I met personally, if I'm not mistaken, Eric Lerner. That was in 2008. A conference, Crisis in Cosmology conference in Seattle, USA. And I also met personally Alexander Unziker in Germany in 2023 when I was there doing these translations of Weber's work. So we did have a chance to meet in Munich, so that was very great. And
was that at an event, or he reached out to meet you, or how did that happen?
Well, I was working in Germany for 3 months at Augsburg University on the translations from German into English of Wilhelm Weber's works. So, and that was very nice, because then last year we could publish volume 5 of these translations. So it was a very...
Was Alexander just walking down the street and you bumped into him, or how did you guys end up getting together?
We did had some exchange by emails, and then one day when I was going in Munich, I don't remember the reason, then we met at the train station, and then we did have a wonderful coffee together there in a restaurant nearby. It was very nice indeed. And I also, if I'm not mistaken, I met Uni Krishna maybe in 2002 or so in a conference in India, maybe, organized by Amitabh Ghosh long ago. Maybe it was in 2002, if I'm not mistaken. So it will be great to meet all of these people again, and both of you for the first time.
Yeah, technically in person. Yeah, I wanted to tell people, if they're listening right now, that they should go back and watch our first couple of conversations with you, because we've explored Weber's work on electromagnetism, mostly just it's not electrostatics, but
Electrodynamics.
Electrodynamics. Okay. Yeah.
And so now, and also to tell the people, because that time, so now we have 5 volumes of his works translated and commented from German into English. And they are, all these 5 volumes, they are available in my homepage. People can download it for free. And they can, if they wish the printed copy, they can go in Amazon. So that's very nice.
This is, I feel like, almost passé to ask in a scientific context. But if you had to, in a minute, describe what you found in Weber's works, could you?
Yes, because it is what attracted me in the first place to Weber is that it is a force law, just like Newton or Coulomb, which depends on the distance between the 2 charges, but also on their relative velocity and relative acceleration. So these are relational magnitudes, as I call it. In Lorentz force law that we learn in the textbooks, QE plus QV cross B, charge times velocity times the magnetic field, it appears a velocity which nowadays is interpreted as the velocity of the test charge relative to the observer, which doesn't make sense to me, because it is interacting with other charges, not with the observer or frame of reference. And so for this reason, when I found about Weber in History of Science, I began to work with that, and then I was discovering many jewels, one after another. And so...
I think that there's something really interesting about this translation idea, that it's taken until 2025 to translate these works, because it seems to me, as I'm learning more and more about the history of physics, that there was a big divide linguistically between the Germans and the English.
Yes, sure.
And politics and world wars got in the way.
Sure. You see, Shiloh, when England became a world power and so on, the works of Coulomb, Ampère, which were in French, they were never translated into English. Only now they have been fully translated and commented into English. And the same happened with the works of Gauss and Weber on electrodynamics. Weber published 6 large volumes of his experimental work, some of them together with Gauss, some of them alone. They have more than 3,000 pages. I don't know, maybe 50 papers or so, some of them with more than 100 pages. Only 2 or 3 or at most 10 of them have been translated into English. And of his 8 major memoirs on electrodynamics, only 1. All the others, never. And so, and the same with Ampère. His main book on electrodynamics was never translated into any language until 2009, when we did make a Portuguese translation. And then in 2015, we made an English translation.
And that's super wild, because these are, at least Ampère is somebody who would be considered a kind of, he would be considered a winner. I was going to say there's a parallel here with history. You know, history is written by the winners. And so we get this one story usually about history in history classes, right? Especially at an elementary level. But physics, that's really strange, because some of these people are actually heroes of physics, but we don't have access to their original writing in our classrooms, which is...
Well, we need to be able to filter, because we're like, look, there's a mathematical law that lets us do something, but all of the stuff that he said as he was deriving the law, that just seems like it's extraneous. Like, why do we need to know that?
Yeah, you are correct, Anastasia, but there is one point which Shiloh is precise, because sometimes when we learn the textbooks, they make a deturpation of the work of these authors. For instance, what every textbook calls Ampere's circuital law, the line integral of the magnetic field in a closed loop is proportional to the current which flows through the loop. Ampère never wrote such a law. He did fight against something circulating around a current carrying wire, like a magnetic field. He fight against it. He proposed a force law along the straight line connecting the 2 current elements, which Maxwell called should always remain the cardinal formula of electrodynamics, the most important formula. But it disappeared from the textbooks. The one which appears is the so-called Grassmann-Biot-Savart, does not comply with action and reaction. And Ampère was fighting for action and reaction, Newtonian approach.
Okay, so my question then is this. If it works, and this is a devil's advocate question, understand that I ask this in order to set the stage. If it works, what does it matter? Like, if he was fighting for a different perspective on the law and he wanted the law to be formulated differently, and the thing that's on the books is it does not contain within it action and reaction, but it works, so what? Like, why do we need to think of action and reaction?
Because this other approach can lead us to new phenomena, to new effects. They are not always compatible with one another.
What are the new effects that you imagine that it could lead to?
For instance, if we have 2 current elements which are aligned like that, and along the straight line which connects them, according to the law of the textbooks, Grassmann's Biot-Savart, they do not exert a force on one another. According to Ampère, they should repel one another. So people have been doing experiments on these longitudinal forces, even nowadays. I did work for 1 year in Boston 1991, 92 with Peter Granot. He did make many experiments on these longitudinal forces. Nowadays, he's died some years ago, but his son, Neil Granot, he's still working in Oxford and doing experiments on these longitudinal forces, trying to distinguish from the Grassmann Biot-Savart. So this is very important because these things, they have not been settled completely.
What are they finding in those experiments? That there is an appreciable force that's not captured by the classical?
Yes, and they can measure that, but there is always discussions on the interpretation and so on. But you see, the important point is that they are going to the laboratory. And so it's very nice. And the same is happening with Weber as well.
Oh, and in what ways is it happening with Weber as well?
These people are going to experiment and trying to find new phenomena which happens only in Weber and not, for instance, in this Lorentz force law and so on. This is the interest which people are getting nowadays once more. They are reviving this paradigm of Newtonian paradigm of Coulomb, Ampère, and Weber, which is opposed to the paradigm of Faraday and Maxwell. And this is very important.
Can you help me understand why the winners in that story were the winners? Like, why are we left with Lorentz and Faraday and Maxwell and Civil?
It's a complicated story, Shiloh. But
take your time.
Yes, some of the main opponents of Weber did live at the same time as Maxwell. He was born before Maxwell and died after Maxwell. So they were contemporaries. Maxwell quoted many times Weber, always praising Weber highly because he was an excellent experimentalist. But Maxwell did want to follow the paradigm of field, which was created or initiated by Faraday. But in his textbook, he's always comparing the two paradigms. But then Weber had two main opponents. In Germany, it was Helmholtz. Helmholtz was very powerful. And in the United Kingdom, it was William Thomson, Lord Kelvin. They were the two main opponents.
The thermodynamicists get involved.
Yes. And there is a book by Kelvin and Tait, T-A-I-T, in which they say that Weber's law is even dangerous because it is too good. It complies with action and reaction, conservation of energy, and so on. And so it is a very dangerous idea. And it were these two guys, Kelvin and Helmholtz, that when there was a meeting in France, the first international congress to decide the names of the electric units. It was in 1881 when they decided to call Coulomb, Ampère, Ohm for resistance, Faraday for capacitance, Coulomb for charge. So at that time, due to Weber's work on the measurement of force between currents and so on, people utilized the name Weber as a unit of current. But then in the last minute, due to a suggestion of Helmholtz and Kelvin, they decided to delete the name Weber purposely and to introduce the name Ampère, which we utilize even nowadays. For the unit of
hold on 1 second. I got to understand this Helmholtz-Kelvin thing. So these thermodynamicists, they were using fluid flow equations to describe the motion of heat. Was heat was not, we did not yet have the kinetic theory of of molecular theory of heat, right? At that point.
No, and that it was beginning to be developed, but they were mainly working with the continuum, with like a field approach based on the continuum. And Weber, he was always like a molecular guy, particles. Yeah? So he was always of this kind. And so Weber, in his, as I said, 6 large volumes, I don't know, 3,000, I don't the number of pages, 3,000 pages. He never mentioned, not even once, the word field. He never worked this paradigm. He only talked about current, charges, velocities, velocity of circuits, or drift velocity of the particles in a current-carrying wire. He never utilized a magnetic field, flux of a magnetic field, time, the temporal variation of a magnetic field, never.
So was Ampere the opposite in the sense that he was more
Ampère
focused on
was
fields?
the same because Ampère didn't talk about fields. This idea of fields, it began with Ørsted, when he found that when he did pass a current in a wire and a magnet, it was deflected. Ørsted, in his mind, explained this not only with charge moving inside the wire, but he imagined that there was an elliptical flow of charge around the wire. And these charges would press the magnetic poles. So this is the first idea of something circling around the current-carrying wire. It was Ørsted.
And Ørsted is the one who did the deflection experiments where he brought the compass to the wire and discovered that there's deflection.
I think that's what he's describing right now.
Yeah, I just wanted to clarify for those who are listening that like this is a canonical experiment that tells us that there's something circulating. What do you mean?
Like, what's the alternative to something flowing that's causing the magnetic?
It is Ampere's alternative, Shiloh, that we have current in the wire and current in the magnet. The magnet has microscopic currents, which we call molecular currents or Amperian currents. And so there is action at the distance between current in the microcosmic wire and the microcosmic currents in the magnet. So, and these actions, according to Ampère, they are central.
So is he removing magnetism from the equation? He's almost
yes, exactly.
I see.
He said that this idea of magnetic fluids, north magnetic fluid, south, these are superfluous. We only have interaction between currents.
I see. I always thought it was kind of strange that we call it.
He made the first
electricity and magnetism, and they're so intimately related as two sides of the same coin. I always thought that was strange, and I just figured it was an artifact of discovery.
And so it was
doesn't it force you
Ampère.
at some point, though, to do the same thing with light, though?
Yeah,
right? Yeah. Because you have to put these bins somewhere, because if you treat light and electromagnetism as being exactly the same thing, then you're kind of hosed, because light clearly is something that's a little bit different.
A little bit of both, too.
A little bit of both.
Let me talk about these two things because they are very important. So the first unification of electromagnetism, textbooks always talk about Maxwell, he unified, but it was not, it was Ampère, as you said, Shiloh, because he did unify the interaction between two currents, which he did call electrodynamics, magnetism, interaction between two magnets and the magnet and the ears, and electromagnetism, which was this experiment by Ørsted, that a current deflects a magnet. So he could unify these three branches, assuming only interaction between current elements, and assuming that in a magnet or in the ears, there are currents flowing.
Is there any way to test that? Like, is there any way to show that inside of an isolated body, a current remains flowing?
Yeah, sure. Many experiments about the... Ampère himself, he made many. the same experiment in which you deflect a magnet, he put a circular current carrying wire, and it did deflect as well. So all these effects he made only with currents or with currents and magnets. The attraction and repulsion between two magnets, that was his first experiment.
But do you see what I'm saying? Like, usually we think of current as being an open system where some energy is being supplied to the system to drive the current. But the idea that an isolated body like a magnet would have a current without being open to an energy source, is there any way to validate that statement? Because it makes sense.
Yes.
Like it makes sense, but is there a way to know whether there's a current inside of this magnet?
This was the point of view of Weber, because in a macroscopic circuit, we need to have a battery to create a steady current, because the wire has resistance. But the microscopic currents of Ampère, they last forever. So you don't need to have a macroscopic battery in each atom. So to Weber, it was because there was no resistance. So he did assume that the atoms, you have a nucleus, which was positive, and the electrons, they were moving around in an orbit, just like a planetary model. And so there is no resistance. So it will be there forever until it interacts with other currents. But going back to Anastasia.
Wait. Hold on. I understand that. Like, he made this assumption. I totally understand it. It makes perfect sense to me. My question is, can that be empirically validated?
Well, okay, so, and I think that I can zoom out of that and maybe give it a little bit more context, because there's a bunch of different equations in physics that take the same form for like fluid transport. So the flow of liquid looks the same as the equations for the flow of heat, and yet they're different, and there is a process by which we determined that they were different, and it's many abstraction layers of thought that get us down to like what is heat and what's happening inside of the atoms, etc. And the question is, like, can you actually experimentally prove that? Or is this something, even with the heat and fluid relationships, that we have determined philosophically and inductively, but cannot stick a detector into a system to be able to say unequivocally that this is absolutely different? Is this the question?
And I'm totally fine if that's the case.
Yeah, but that's the question.
I'm totally comfortable with that as a hypothesis. I just wonder if it's a statement that can ever be empirically validated. I don't think that all of reality can be empirically validated.
No, not all of them, but some of them we can test. And Weber did test these ideas of the motion. He didn't know about the electrons. They were discovered after he was dead. But about this planetary motion, he could explain diamagnetism based on these. And he made many experiments to show that the existence of magnetic fluids could not explain the diamagnetic phenomena. It was necessary, these microscopic currents of Ampère.
And diamagnetic phenomena are, for folks that are not...
that two magnets, they attract, or a magnet attracts a piece of iron. But diamagnetism, you have repulsion. And it's a very tiny effect. And Weber showed that this effect is that when you bring a magnet close to a diamagnetic material, you induce microscopic currents in this material. These are very small currents, but you can measure them, and Weber was very precise. And then these induced currents, they tend to create like opposite poles. So that just repel, or the currents will flow such that the two currents will repel, to express more clearly, not based on magnetism, but based on currents.
But this is the way that people actually think about magnetism at the highest levels right now, though, right? Where it's like inside of a material, the atoms are organized, their spins are parallel to one another, and that's what gives you I mean, you still have to deal with action at a distance, which we haven't quite covered yet, but I think that the idea that the atoms inside the substance are somehow aligned with one another and functioning together as a whole is the answer we got to, several hundred years later. So it's kind of incredible that he was able to derive that from first principles without even the idea of, what the hell are atoms?
Yes.
I still think people wouldn't chalk it up to currents necessarily. Like this paramagnetic phenomena or diamagnetic phenomena, depending on the electron spin state, it's kind of taken as a piece of magic that relates to the spin state of the valence electrons.
Okay, well, so let's zoom out a second, because if you think about current as being the flow of electrons, which is obviously like problematic in many ways, which I'm sure that we'll get to at some point, but the motion of the electrons of the atoms in a magnetic substance being properly oriented seems to fit into the same category of phenomenon as current in a circuit, in the sense that it's some kind of motion to do with the atoms. Right? Like, I think that if you
propagation of charge.
Propagation of charge.
Motion of charge, but let me just go back, because Anastasia, you were talking about, when we talk about unification, you mentioned about optics, that we should also connect optics. Also, in the textbooks, they say, Maxwell, the great Maxwell, he saw that this Ampère circuital law, it was incomplete because it was not compatible with conservation of charges. Then he introduced the so-called displacement current. And then he did obtain the wave equation. And then he unified electromagnetism with optics. Okay? That is in every textbook. But they don't mention where in this displacement current, which Maxwell introduced, is 1 over c squared, derivative of the electric field with the time. So, but where did Maxwell take this constant c? This constant c had been introduced by Weber 20 years before, in 1846. And the first person to measure this constant c was Weber himself with a collaborator, Kohlrausch, in 1856.
Are we talking about the speed of light?
Yes.
Okay.
Yes.
Okay. How did they measure the speed of light?
And they did obtain the speed of light.
How?
They didn't measure any velocity. That constant relates Coulomb's law with Ampere's law. So Weber and Kohlrausch, they did measure the force between two charged spheres with Coulomb's torsion balance. So he could know the amount of charge. Then he did discharge one of them through a conductor to the ground. And this discharge was very fast. When the discharge, it deflects a magnet nearby. So he knew the amount of current which was flowing. And so by these two measurements, he could relate Coulomb and Ampere's law, which he unified.
Basically just figuring out how much current was required to accelerate that magnet so he could back calculate the velocity of light as a result of it?
No. The light velocity didn't appear, has nothing to do. It was a constant, purely electrodynamic.
But it does happen to be the speed of light.
But this was discovered later on. At that time, no one knew about that.
We should cover this more deeply, because this is astounding, right?
Yeah, I think what I'm trying to say is that, I'm working off of my contemporary understanding of why there's a speed of light at all, which for me is relates to the deformability of the medium itself, just like a speed of any deformation is limited to some material. And so when you talk about what the electron discharge is, I'm thinking that it's also limited by this same deformation of whatever substrate the atoms are made out of, or this substance upon which all of this dynamics is playing out. And so I'm thinking that he may not have realized that was the speed of light at the time.
He didn't measure any velocity. He just measured
But
the force between two charged spheres and the torque that a certain current caused in a magnet nearby.
but he did get a velocity at the end of the day.
He did obtain the value of his constant, which he had introduced 10 years before, which has the units of a velocity. But the value had nothing to do with light.
Yeah.
But then he found it the same as light velocity. Not only that, that was before Maxwell. Maxwell was in high school. And then that was in 1856. Maxwell did introduce his displacement current in 64, 7 years later.
But he must have thought it was the velocity of electricity or something.
One last point, Shiloh. Then, so in 1846, Weber introduced his constant C. 10 years later, he measured this constant C and found it light velocity. And then 1 year later, in 1857, he and Kirchhoff, they did deduce. Weber created the first working telegraph together with Gauss in 1833, many years before. But then in 1857, Weber and Kirchhoff deduced theoretically how is, if you perturb a current in a wire or the amount of charge, how does it move around the wire? It is a wave. So he did calculate and he did obtain the telegraph equation. It was 1857. And when there is no resistance in the wire, the telegraph equation goes back to the wave equation. So the first to obtain the wave equation in electrodynamics was Weber and Kirchhoff, not Maxwell. That was 7 years before Maxwell. So when Maxwell in 1864, 62 introduced the displacement current, he took that constant C from Weber's electrodynamics. He knew the value of this constant by Weber and Kohlrausch experiment, which gave light velocity, and he knew that he could obtain the wave equation with this constant because Weber and Kirchhoff had obtained that 7 years before. Everything was known to Maxwell, but nothing of this appears in the textbooks on electromagnetism nowadays. For this reason, these translations are so important because now people can read the original works in these 5 volumes. We have also the translations of Kirchhoff's papers, 1857, before Maxwell. We have the translation of the first ever measurement of this constant C by Weber and Kohlrausch.
Okay, so let's
I want to just
unpack.
catch people up though, because I think what's profound here might have gotten buried. Because I think what's happened is he discovered the speed of electricity, and it could have been called C could have been called the speed of electricity, but it was called the speed of light later when it was discovered that this constant was also the same as the speed of light. I never knew that. That's amazing. First of all,
So hold on. The experiment is that you have 2 charged spheres on a torsion balance and a wire that can ground one of the charged spheres and a magnet that can deflect. Is the measurement, is C derived from the amount of time that it takes the magnet to deflect after you ground the sphere?
It has to do with the units of charge and the units of current, because in Weber's law, he did unify the laws of Coulomb, Ampère, and Faraday. And to unify, he did need to generalize Coulomb's law and to introduce a component which depends on relative velocity between the charges and relative acceleration. And there did appear a constant there which has to do with the units of charge and current. Has nothing to do with velocity, but it happens to have the unit of a velocity. Only later on did they realize, when he made this measurement for the first time, they realized that there was light was connected with electrodynamics. It was after this experiment, which was made by Weber and Kohlrausch.
Okay, I think that makes sense for
I don't
everybody.
know, Shiloh. Today we should talk about a history of the cosmic background radiation. Shouldn't
Oh
we
no,
talk
you want to do
about that?
CMB? Are you sure? Okay.
Yes. Let's go to this.
Before we sat down, Shiloh was like, we should make sure to avoid the CMB. It's like, I don't want to hurt anybody's feelings.
No, we can do the CMB.
Because the top they should be the history of the cosmic microwave background radiation and Hubble's cosmology, which will be some of the topics which will be discussed in the conference in Demystify 2025 in Portugal this June. And so shouldn't we go to this subject? So
I want to see if we can connect these two disparate subjects, where I think that there's something fundamental about the nature of science and the progress of science that we can see in electrodynamics and our understanding of where these phenomena are coming from and the relationships between different kinds of phenomena that is probably also playing out in the field of Big Bang cosmology, where there's something that can be learned by analogy between fields that seem totally unrelated to one another.
Well, can I summarize what we've talked about so far in this historic encounter is, on one side, you have this fluid dynamics, statistical expressions, fields, mathematical representations. And on the other side, you have these people who are, I know that they use the word particle, but they're really, what they're looking for is a material explanation for what's actually happening.
Yes, Shiloh, you are correct.
And so
Science.
the sort of mathematical
and an idealistic two sides.
Perfect. That works for me. And so I think we can come back to this idea of idealism, maybe positivism versus realism. That will make its way back once we get into cosmology, if we want to turn to that at this point. So yeah, let's talk about it. I think why Anastasia said I was scared of talking about it is because I'm not...
I didn't say you were scared of talking about it. I just said that you were ready to throw some punches.
No, I'm not convinced it's cosmic, but let's talk about it. Let's talk about the history a bit.
Yes, and the two subjects, they are connect also on the history. Because for this reason, to me, history of science, history of physics is so important. Because when we read about in the textbooks about cosmology, for instance, they always say, oh, there were two paradigms in cosmology, the Big Bang cosmology and the steady-state cosmology of Hoyle, Narlikar, and Bondi. And then the discovery of the cosmic microwave background radiation, which had been predicted by the Big Bang, but not by the steady-state theory of Hoyle, Narlikar, and Bondi. So the discovery of the cosmic microwave background radiation of 3 Kelvin, which had been predicted by Gamow before its discovery by Penzias and Wilson in 1965, decided in favor of the Big Bang, and the steady state was eliminated. This is only a partial history of science, because there is a third model of the cosmology, which the textbooks, they don't mention. Because this is steady state theory of Hoyle, Bondi, and Narlikar, it has something in common with the Big Bang. It also accepts that the redshift is due to a Doppler effect, when the source and the detector, they are moving relative to one another. But they said, well, okay, the universe is expanding, but there is continuous creation of matter, so that the density is always the same as a function of time. The universe is expanding, but there is creation out of nothing. And so
So
But
like
we
the
still-
galaxies are pushing apart from each other, but there's new ones forming
Yes,
also.
yes.
And so things do appear to be moving apart from each other, but there's new things happening. So it's like
Yes.
kind of these
So,
bubbles popping.
but
all the
this
time.
is the steady state of Hoyle and Narlikar and Gold versus the Big Bang. But there is a third alternative in which there is no expansion. And the redshift is due to some kind of interaction between the light of a distant galaxy and the intermediary medium.
Love it.
And this third alternative is not discussed in the textbooks on cosmology and astronomy.
I would
And
say
so-
that it is generally laughed out of the room the minute that you mention
We
it.
do it in my astronomy class. Come
Well,
on.
yours is a
I
unique
would like
case.
to
Well,
have
it's you-
been your student, Shiloh, because in
I
all
wish
the
you were my
others,
student.
they don't. The teachers, they don't mention this third alternative.
Well, is it kind of wrapped up in the concept of tired light sometimes?
Yes, it is exactly, because this idea that if light interacts with the medium, the energy of the light decreases because it is like heating this medium, and so the energy of the light decreases, and they call it tired light. Okay, but so now let me go back. So the first point is not only there is this prediction of the temperature by Gamow based on the Big Bang, but when we read their original papers, what we find, Shiloh and Anastasia, is fascinating. Because the first published prediction of this temperature of the cosmic microwave background radiation was not made by Gamow, but by two of his students, Alpher and Hermann. And they did publish a paper in 1948. And based on the Big Bang, that in the beginning, it was very hot, and then it was expanding, and it was cooling as time goes by, and so on. And nowadays, they did calculate what is the temperature nowadays. Then in 1948, they did publish 5 Kelvin. Next year, the same students of Gamow, Alpher and Hermann, if I'm not mistaken, it was in Physical Review or something like that. So in 1949, they said bigger than 5 Kelvin. Then the first paper by Gamow, it was published in 1953. It was in a Swedish magazine. And in this paper, Gamow said 7 Kelvin. So they began with 5, greater than 5, 7. Then Gamow did publish a book called The Creation of the Universe. This title is very religious. The creation of the universe. The universe was created out of nothing. So this book was published in 1952, but there was a second edition of 1961, just 4 years before the discovery of the cosmic microwave background radiation by Penzias and Wilson in 1964. So in the second edition of Gamow's book, The Creation of the Universe, there is only one page where he mentions the temperature of the present-day universe based on the Big Bang. And guess it, the temperature he gives is 50 Kelvin. So they began with 5, greater than 5, 7, and 50. Then 4 years later, Penzias and Wilson found 3.1 Kelvin.
And everybody's like, we predicted that.
Yes, and then Gamow came along and said, I had predicted that. It was
I've got friends like that.
20 times higher he did predict. 20
Amazing.
times. It was not 100%, it would be 6 Kelvin. But it
Yeah.
was 20, almost 20 times higher because they found 3. And the last prediction was 50. Many times, almost. So
How did they square that? Like, what happened? So the Penzias and Wilson find the signal.
Propaganda, Anastasia, just propaganda. Because then is exactly propaganda. Because then they met and they did. There are some correspondence between Penzias and Gamow and so on. And Gamow was complaining because Penzias and Wilson, they didn't quote his earlier predictions and so on. And he was always saying, there is even a conference in which Gamow said, well, there is a saying that if people lose a nickel, and if someone finds a nickel, you cannot prove that that lost nickel did belong to that person, because it may be for another person. But then Gamow said, but I lost a nickel just where they found one. And then in this conference, everyone clapped. Oh, great Gamow, and so on, and so on, and so on. But things are even worse when we read this third paradigm, which I was mentioning, in which the redshift is not due to motion, but it is due to interaction. Then there are many people who made predictions much better than the Big Bang and much earlier than the Big Bang. And nothing of these appears in the textbooks. For this reason, I am so happy that Anastasia and Shiloh, that you invited me for this online conversation and that you invited me to present these ideas in this conference in Portugal, because people need to know about these things. They are hidden from them, especially from young astronomers, from young cosmologists. The oldest prediction I know of was made in 1896, before Gamow was born. Gamow was born in 1904. So 8 years before, there was a guy called Wilhelm. He published a paper in French in a journal called La Nature, the Nature. And in this paper, it is called The Temperature of Space. What did this Wilhelm make? He did utilize measurements by others and by himself of the background light of the stars. Okay? For which the stars which belong to our galaxy. And then he said, if a body absorbs this energy, it will heat, but then it will begin to radiate, but then it will reach a temperature in which the amount of energy which it absorbs is equal to the amount of energy which it radiates. And then its energy does not increase any longer.
Like thermal equilibrium.
Thermal equilibrium, exactly. And then he did utilize a very famous law of thermodynamics, which is called the Stefan-Boltzmann law, which says that if you have a body and if you calculate the amount of energy which it radiates in all frequencies, it is proportional to the force power of the temperature. Stefan did obtain this law in 1877, 1879, and Boltzmann, which was his student, did deduce it theoretically in 1884. So Wilhelm did utilize Stefan Boltzmann's law to calculate the temperature of this body, which absorbs the energy from the background of stars and radiates it again. And this Stefan Boltzmann law is a law of blackbody. When he did put the numbers from the measurements of this background, he obtained 5.6 Kelvin as an upper limit. You see, this is before Gamov's birth. And who was this Wilhelm? It is someone who won the Nobel Prize in Physics in 1920. He's a very important physicist. He was president of the French Society of Physics. He was the president of the Bureau of International Measures. And he did won the Nobel Prize in 1920 for his high precision measurements. So it's a very important guy.
So in the sense, in his model where there is this thermal equilibrium, did he propose what was at thermal equilibrium? Is it just like space dust? Like, what is the body that's radiating at 5 Kelvin?
Just a body which has a size large enough so that it will absorb energy from the background and radiate it back. So
like rocky planets and asteroids.
Yes, a planet, or even if it was like water, it could be just like 5 meters diameter. So if it is just a particle, not. But if it is just like a rock of 10 meters diameter, that it will reach this temperature. And this is the temperature which he called temperature of space.
So he's basically like the rocky materials, the rocky bodies that are in space, if they are absorbing starlight, this is the temperature of the radiation that they would. Got it.
Yeah.
Okay.
It's a minimal size because just from antenna theory, you need a pretty big lattice to emit microwave signals. I like it because
But
I like it. I mean, I like it on its face because it actually implicates the stars in the source of the black body radiation, as opposed to some plasmatic recombination moment at the beginning of the universe, which for me has always been that. This is what I was saying originally: is the problem being that gaseous plasmas don't seem to make black body spectra at all. And that's really strange that everybody would be pointing to this moment at the beginning of the universe when you have all this gas light, essentially.
It must be a solid body or a fluid, water, or something like that. Not a gas.
I also had a theoretical issue that I kind of came to the other day, which I told Shiloh about, that I want to try out on you, which is that if you have the Big Bang and everything is at the same temperature and there's nothing outside of this cluster of matter that has just been born, how can it radiate heat? How can it cool? Because there's nothing outside of it. You have to have photons that are able to be just shot out into space. But if you take photons to be a transaction between atoms in a condition where everything is the same temperature, you can't cool, right?
I could discuss this last time, but I prefer not, because I myself, I don't believe at all in the Big Bang. To me, this is just fantasy. I just like to continue this history, because this is very important, because people, they are not aware of it. The second prediction I found, not only prediction, but based on measurements, was a similar reasoning of Wilhelm made by Eddington. He has a book, The Internal Constitution of Stars, 1926. Then it has, I believe, the final chapter of this book. It has a section which the same title as Wilhelm's paper, which is called The Temperature of Space. He doesn't mention Wilhelm, but the reasoning is the same. You have the background of stars, you have a body which absorbs that energy, radiates energy back, and reaches equilibrium. Then he utilized Stefan Boltzmann's law and obtained a temperature, just like Wilhelm. But he was working 35 years after Wilhelm. So he obtains a better number, 3 3.2 Kelvin, which is just the same as Penzias and Wilson in 1965. Penzias and Wilson found 3.1 Kelvin in Eddington.
Sorry,
Eddington.
who wrote the internal constitution of the stars? Eddington. Gotcha.
So it was published in 1926. So in the last chapter, it is a section, the temperature of space. And then he obtained 3.2 Kelvin, and he mentions that this is the so-called interstellar temperature. Okay? But you see, Wilhelm and Eddington, they were talking about energy of the background of stars, which belong to our galaxy. Just 2 years before, Hubble, in 1924, he did, the astronomer Edwin Hubble, he was working at Mount Wilson and the observatory with the 100-inch telescope. And then he did discover some Cepheid variables in some nebulae. And by the period of the luminosity of these stars, Cepheid variables, he could estimate the distance of these nebulae. And then he discovered that many of them were much farther away than the background stars. So this is where the discovery of the galaxies did take place. So it was just 2 years before Eddington. But in this calculation by Eddington, he's still talking about the background of stars, interstellar temperature. But then in 1933, there is a German scientist, Wegener. And this Wegener, he was working with cosmic rays. Cosmic rays are rays which come from space. They may be electrons, they may be protons, they may be ions, ionized nuclei, they may be even gamma radiation and so on. And we know that most of these cosmic rays, this cosmic radiation, comes from outside of our galaxy. And then in 1933, this Wegener, utilizing the same idea of Wilhelm and Eddington, but now utilizing the energy of this cosmic ray flux, he did utilize all of this energy comes to a body. This body heats until it reaches a temperature in which it emits the same amount as it absorbs. Then once more, Wegener, utilizing the Stefan Boltzmann's law, he measures the temperature of this body, which is in equilibrium, not with background stars, but with the background cosmic ray flux, which comes from essentially from the outside of the galaxy. And he obtained a number 2.8 Kelvin, which is extremely precise. Our present day value of the cosmic background radiation, which is 2.75 Kelvin. And this was Wegener in 1933, much before Gamow, much before Alpher and Hermann. Then 4 years later, and this Wegener is very famous in research of cosmic rays. He was a German scientist. He was president of the Max Planck Institute of Cosmic Rays, and he was known for his high precision measurement in balloons and underground. Very, very famous guys. 4 years later, Nernst, the father of the third law of thermodynamics. He quoted Nernst's measurement of the temperature, of this temperature of 2.8 Kelvin. And Nernst was specifically against the Doppler interpretation of the, he was in favor of an infinite universe without expansion. Nernst did propose that the photon coming from a distant galaxy interacts with the medium, maybe with dust or something, and then it loses energy. And he proposed an exponential law that the variation of the energy is proportional to the energy times the distance. So this gives an exponential law. And Nernst, he did propose an infinite universe without expansion, without Big Bang, which had been proposed by Hubble. Nernst was against. And this Nernst is
can I pause you for just a second just to catch up on one thing? The observation that Hubble had, this Hubble relationship, was not merely that things got redder at a distance, but that they got, I don't know if exponential is the right factor, but they got much more red at a distance. It didn't seem to be a linear relationship.
Not for Hubble. For Hubble, it was a linear relation.
Oh, okay, my bad.
But the greater the distance, the greater the velocity. Okay.
The greater the velocity, okay.
Yes,
okay.
yes.
So, yeah, so that's the nonlinearity of the situation that leads to the expansion.
Yes, but you see, that was Hubble in 1929. But Nernst knew about Hubble's law, but he was openly opposed to this interpretation that the redshift is due to a Doppler effect, motion. He said, no, it is due to some kind of interaction of the light from a distant galaxy until it reached the Earth. And this interaction, and he believed in an infinite universe without expansion. And this Nernst is not only the father of the third law of thermodynamics, but he also won the Nobel Prize in the same year as Wilhelm. It's fascinating because when
what did Guillaume? I don't know how to say that word. I just tried poorly. Guillaume.
Guillaume.
Okay, what did Guillaume win the Nobel Prize for?
For he did discover some nickel alloys, Invar and Livar, which have very special properties, which allowed him to make extremely precise measurements in thermodynamics.
Okay.
I have even here, I can read the text of why he got the Nobel Prize. I have here in my hands.
Yeah, why not?
It says, in recognition of the service he has rendered to precision measurements in physics by his discovery of anomalies in nickel steel alloys. That was Guillaume, 1920, in physics. And curiously, Nernst, the father of the third law of thermodynamics, in the same year, he got the Nobel Prize, but in chemistry. But you see, this Nernst, he utilized this measurement of Wegener, of this cosmic ray measurement of Wegener and of this temperature of 2.8 Kelvin. By the way, Shiloh, for those who are watching us now, I published in 2020 with a collaborator of mine, Marcos Neves, in the American Journal of Physics, a complete English translation of this 19 1896 paper by Wilhelm on the temperature of space, where he arrives at this upper limit of 5.6 Kelvin. So anyone which goes in my homepage, there is the paper is available there in PDF, a complete English translation of this French paper by Wilhelm. The translation was made by a colleague of mine, Roy Keyes of Canada.
Amazing.
And the paper is together with this collaborator of mine, Marcos Neves, with whom I did also publish papers on this, the topic that we are discussing now, on the history of the CMBR temperature.
That's really cool. Well, I can link that in the description for people who want to read it. I'm going to go read it myself. It sounds really fascinating. Thanks for doing that work.
But let me continue, because these are very important people. In 1954, there is a German astronomer, Finlay Freundlich, who did also was working with something related with Einstein and so on. And he has a paper, 1954, also trying to explain not only the cosmological redshift, but there are anomalous redshifts. For instance, in the sun, the star closest to us is the sun. If we look at the center of the sun, it has a certain redshift. When we move towards the limb of the sun, the redshift increases. This is called the limb effect. So, and this is not explained by Doppler nor by gravitational redshift. It must be something else. There are some anomalous redshifts in O stars, A stars, white dwarfs, different kinds of stars. So this Finlay Freundlich said it should not be Doppler. He proposed something which is similar, that the variation, that the redshift is proportional to the force power of temperature of the radiation field and the distance in which light needs to propagate. Once more, we see this Stefan Boltzmann's law of the force power of the temperature. But now, Finlay Freundlich proposed that empirically to explain this effect of the sun from center to limb of these A stars, O stars, and so he could find the value of this constant, that the redshift is a constant times the force power of the temperature times the length. After he found this constant, then he proposed, let us assume that the same effect explains the cosmological redshift, which Hubble found. But let us assume that it is not due to Doppler, but due to this effect which he was proposed in 1954.
Can I ask you a really quick question? For the sun, is the distance just the length of the radius of the sun? Is that the difference in the emissions from the normal and those from the limb?
What appears is the arc of the sine of the angle in which relative to the center of the sun. And when you see, this is how the distance a light needs to travel through the atmosphere of the sun.
Mm-hmm.
It follows this arc sine of the angle relative to the center up to the limb.
I see. So it's just the path through the atmosphere at the end of the day.
Yes,
Gotcha.
yes. And so it must be something there which causes this redshift. So it's fascinating, because even this arc sine shows that it is interaction in the atmosphere of the sun. This is very interesting, Shiloh. And this has been pointed out by this Finlay Freundlich and others.
I have a question.
Yes.
And this might be a dumb question. Is this similar to the reddening of the sun as it sets?
No,
No, totally different.
It is another effect because this reddening of the sun when it sets is not of the spectral lines. Is the sun as
It's like
a whole?
a filtering effect.
Got it. Okay.
Yes, filtering effect. Yes, due to the atmosphere.
Redshift, by the way, just for people who are listening, because this confused me for many years before I started studying it really intensely. Redshift applies to all of the lines in a spectra, right? So you're not just talking about some of the lines moving. And then oftentimes when you see other ways of reddening, it's because you're filtering out the blue light, something like that. I was confused about that when I first started studying these things.
Yes. And me too. It's not simple question. But then going back to this Finland Freundlich, so 1954, before Penzias and Wilson, 1965, okay? So when this Finland Freundlich proposed the same mechanism for the cosmological redshift of the Hubble's law, instead of Doppler, he proposed this mechanism. And then he could calculate the temperature. And then the temperature which he did obtain were a lower and a higher limit. The lower limit was 1.9 Kelvin, and the higher limit was 6 Kelvin. You see, Guillaume 5.6, Eddington 2.8, 3.2, Hagener 2.8, Finland Freundlich between 1.9 and 6. Everything very close to what was found by Penzias and Wilson. And many of these authors, they were against the Doppler interpretation and in favor of an infinite universe without expansion, without a Big Bang. I just want to mention two other authors which came before Penzias and Wilson. In the same year, 1954, Max Born, he quoted this paper by Finland Freundlich and said, if this mechanism is at work, then redshift must be linked to radio astronomy. This is a fascinating prediction because Penzias and Wilson, 11 years later, when they did discover the CMB radiation, they were working with a horn reflector antenna to study radio astronomy. We see, not only did they get the temperatures very close to this 2.75, but they even said it is connected to radio astronomy. Then we have also de Broglie, the French guy who won the Nobel Prize. Oh, this Max Born, when he published this paper in 1954, is the same year in which he got the Nobel Prize for his work in quantum mechanics. You see,
I mean, given all of this, it's really remarkable that Penzias and Wilson make the report of this observation, and then in the same journal, the same volume of the same journal, somebody else says it's because of the Big Bang. And
yes,
then all of a sudden they're getting...
Robert Dicke. They didn't even publish Dicke's paper before Penzias and Wilson, which is strange because...
So I kind of want to understand the political backside as to why all of this work has been done that points to thermal explanation for it based in stars, and then all of a sudden it's being turned into this proof of the beginning of the universe. Hey there, pardon the interruption. I need to ask you a favor. Please consider supporting this project directly. We don't have sponsors, we're not selling stuff that we didn't make, and the only way we can keep doing this is if you support us directly by giving us just the smallest donation over at patreon.com. You can also get access to exclusive content and join our weekly discussion groups. So I would love to see you there. It's patreon.com/DemystifySci. All right, let's get back to the conversation with André. First of all, before we jump back in, I want to say I'm really, really excited to be talking about this because I actually have to give a lecture on the CMB on Tuesday at the university, and so I'm really glad to have this perspective. So one thing that's always troubled me, and this makes it even more troubling, is that as soon as Penzias and Wilson published this data, we have the advancement of the explanation for it, and then everybody jumps on board, and all of a sudden cosmology is in physics departments, and it's just taken for granted that now we are studying the CMB as an echo of the Big Bang. That's what it is. How did that happen if there's been so much work about other explanations for it?
Okay, just before I give my own interpretation, it is very important that you, Shiloh, in your class next Tuesday, and everyone who is watching us now, when they hear something mentioning, oh, the Big Bang has been proved because of the cosmic background radiation, which had been predicted before, then anyone should come out and say, no, this is wrong. When we read the history, the latest prediction on the Big Bang was 50 Kelvin, and they found 3 Kelvin. So
how did that happen? That's crazy. There's got to be some political shenanigans behind the scenes.
This is only half of the answer, because the other half is that people working with an infinite universe, without expansion and without Big Bang, all of them arrived at temperatures very close to 3 Kelvin, even before Gamow. And for this reason, we must mention that, repeat that in our paper, in our classes, in our conferences like this one, which will happen in Portugal, for people to become aware and to read these original papers. All of them, they are now in English. This paper by Hegner, this paper by Guillaume in French, it's now in English. The others were written in English by Philip Freundlich, Max Born, and others. So this is very important. And the second point which I would like to point out is that people, when they talk about redshift, only 2 things come in their minds: Doppler effect or gravitational redshift. But there are many sources
expansion
of redshift.
Too, right?
Yeah, they only talk about these 2 because this is what appears in the textbooks. But
do you consider the expansion to be the same as Doppler? Is that the same in your mind? Expansion redshift? Cosmic redshift, expansion redshift, is that the same as Doppler to you?
Yes, because this is how they interpret that. Later on, we will discuss that when we talk about Hubble, but before that, for instance, beyond Doppler, Doppler exists, this redshift exists, it's there. We measured the rotation of some stars, utilize this phenomena and so on. I have no doubt about the Doppler, but I don't think that the Doppler is the cause of the cosmological redshift. There is also gravitational redshift. It exists, I have no doubt. But this is not, to me, the explanation. What is the explanation? I don't have it.
But hold on. What the heck happened? I want to really understand what was happening behind the scenes, where there's this whole body of literature that successfully predicts the temperature of the universe based on stars. And then it's measured, and then all of a sudden there's a coup, and somehow the prediction that was incorrect wins out. How does that happen? Can you tell me about what was happening behind the scenes to make that be the case? It happened
even before, and then we can discuss that when together with Hubble, because that came before that, with Hubble in 1929 and the relativity and so on. But let me just go back. I would just mention here 2 other phenomena which also cause redshift, known to everyone, but which are not Doppler and are not gravitational. One of them is Compton scattering. If we have a free electron, which they exist in space and so on, and a photon comes and interacts with this electron, the electrons goes to one side and the photon goes to another. So this is called Compton effect, because Compton did study this phenomena. So if the electron received energy, the energy of the photon was decreased. So this is redshift. But to me, the Compton effect is not the explanation of the cosmological redshift. But there, just to mention that there are other sources of redshift. The other one, which many people who are watching us should know, is when we have a fluorescent lamp, which we have in our homes. So this phenomena of fluorescence has been known for quite a long time. And the main property of this fluorescent material is that if you heat that material with ultraviolet, for instance, it absorbs that energy and then it emits a different kind of light, which is, for instance, in the visible region. So you emit light which has lower energy and lower frequency, which is redshift. So we have even animals which have this, which are fluorescent. So if we illuminate them with ultraviolet light, they will shine, be bright in, it can be red, for instance. So it is redshift, which has nothing to do with Doppler and with gravitational redshift.
And I think that this story has to be told together, because the CMB and the redshift have, for the last century, been the two main pillars of the Big Bang.
Like the legs of the big monster, yeah.
Yeah, exactly. And so if you're trying to talk about, well, what happened? How did they come to accept the Big Bang as being the answer when they get this temperature? It's like, well, you also have to consider redshift, because this is the other elephant in the room.
Yes, yes. But you see, Charlotte, just to begin to answer your question, how could the people forget about Guillaume, Eddington, Wegener,
Nernst and Born and like all these
Max
people.
Born, and all of these people, because they were already in another paradigm before. They did jump in this paradigm of relativity before that. And so this was not mainstream. Even with these important people who got Nobel Prize, I mentioned here, Guillaume got the Nobel Prize, de Broglie against Big Bang got the Nobel Prize, Max Born got the Nobel Prize, Nernst got the Nobel Prize, 4 of them. The others were also very important. But what they did in cosmology was ignored, essentially. Why? Because even before them, people were already advocating something related with Einstein's general theory of relativity. And that goes back even to the astronomer Edwin Hubble. And then I would like to begin now this discussion about Hubble, because this is important. And maybe if there is time, we can discuss about that in Portugal this year as well.
And the reason that we have to go back to Hubble is because this story of what the universe looks like, it's not like in 1965 when Penzias and Wilson published this measurement. It's the first time that anybody's been like, hey, maybe there's a Big Bang. There are two schools of thought that are fighting underground in order to get to that point, and in order for that point to lead everybody to transition towards the Big Bang. And we need to understand what the history of those two schools was to lead us to the answer of that question, because it's like, it's more complicated than just two papers in Physical Review or whatever.
Yes, it is. And Hubble, as I said, his first major discovery was that when he found some Cepheid variables in some nebulae, then he could discover the distance of these nebulae to the Earth, and found that it was many orders of magnitude larger than the distance of our stars, which then he discovered these island universes, so the galaxies, many galaxies. That was 1924. But then people were measuring redshifts of stars, of the sun, and also of these nebulae, of these galaxies. And then in 1929, Hubble finally published his paper on the Hubble's law, in which he showed that the redshift of the galaxies were increasing linearly with the distance of these galaxies. How? He didn't measure velocity and he didn't measure directly distance. What he did measure was redshift and luminosity of these galaxies. But suppose that all the galaxies have the same luminosity, so the light falls as 1 over r squared or something like that. So we can estimate the distance by the light that we receive. And also with these Cepheid variables, he could also estimate the distance, but he didn't measure with a ruler and anything. So he measured was luminosity and this period of these Cepheid variables. He also, no one measures these radial velocities of galaxies. What you measure is redshift. And then in this paper, Hubble has a figure in which he plots in the vertical direction the radial velocity of the nebulae, in the horizontal the distance of the nebulae to us. And he shows that it is a straight line. The greater the distance, the greater the redshift, or vice versa. And then he mentions in this paper that maybe this is a de Sitter effect. This de Sitter was a Dutch physicist who was working on general theory of relativity. And he had published papers in 1917, 1918, and he found a solution of Einstein's field equations of these, like these expansion and things like that. And so Hubble, when he founded his law, he himself made this interpretation that it was like an expansion of the universe. But soon after that, Hubble, so if you read the newspapers or magazines or textbooks on astronomy and cosmologies, they all say, oh, Hubble discovered the expansion of the universe. Hubble discovered the Big Bang. This is wrong because he only in the first paper mentioned this idea of expansion. But then he himself began to question this idea. And he spent the last 24 years of his life fighting against this interpretation of the redshift, which he himself had proposed in 1829. Why did he begin to question? Because the main reason which made he question this interpretation was the values of the redshifts which he was measuring. If the redshift is due to Doppler, so the velocity of of the galaxy relative to us, if the redshift is very small, much smaller than 1, so the redshift will be proportional to the velocity, just how he find in this graph. If the redshift is much larger than 1, then the velocity approaches light velocity. It has a limit, okay? If we assume a Doppler interpretation, okay? In his first paper, 1929, when he found the Hubble's law, the largest redshift which Hubble and Humanson, a collaborator of Hubble, had measured was 6 times 10 to minus 3, 0.006, which is a very small number, which means that the galaxy, if it was due to Doppler, would be moving away from us with a v over c, where c is light velocity, equal to 0.006, or 6 times 10 to minus 6, which is a very small velocity. However, soon after that, they continued to measure higher and higher redshifts. In 1942, Hubble, so that is 13 years after his first paper, 1942, Hubble has another paper on the redshift. And now the largest redshift which he finds is 0.13 or 0.14, which is still small, smaller than 1, like 10%, 0.1, okay? And that means, but that already means a huge velocity, because when you convert this redshift into velocity, that means that the velocity of flow of this galaxy relative to us is 1/7 of the velocity of light. That is huge. And so Hubble said, that cannot be the case. Why not? Because all velocity, the only thing which moves close to light is light itself, or small particles like electrons, protons, or ions. The heavier or the more massive, the higher the mass of the object, the lower is its velocity relative to the background. For instance, what is the Earth's orbit around the Sun once per year? What is the orbital velocity of the Earth? It is 30 kilometers per second, which has been known for centuries. If you compare this velocity with light, this is 3 times 10 to the 4 meters per second, this velocity, 30 kilometers per second, okay? What is light velocity? 3 times 10 to 8 meters per second. So 1 over the other gives 10 to minus 4, which is very small, the orbital velocity of the Earth compared to light.
Well, so if I interpret the way that people talk about expansion right now, it's not a real motion, right? Because it's supposed to be that matter is being created in these intervening spaces between the galaxies. And so in that sense...
Are you talking about the steady state people?
Well, no, because when we talk about expansion, they think that space itself is expanding. Like, so maybe
yes,
it's
there
not...
are some people who mention that, Anastasia, that space itself is... Anyone
That's what my textbook says, actually. That's why I remember earlier I asked you if you considered the Doppler to be the same as the expansion, because the funny thing is my textbook says it's not. It's like, this isn't a Doppler shift, because if it was a Doppler shift, like Andre is saying, then the speeds would be too close to the speed of light. And actually, I don't know if you were going to get to this, but like these quasars they measure have, if you interpret it as velocity, you're at like 96% the speed of light at some distant range.
So that's what I'm trying to say, is that there's some feature of the model that has modified the interpretation of the data to not be the speed of the galaxies moving away. It's the speed of expansion of the space between the galaxies. And then you have to ask, what is space and how do you expand space?
This is just play of words. They are just words to circumvent the main problem.
Okay, so you're basically look, clearly this has to be Doppler, and it doesn't make any sense if it's Doppler. And so what's happened is that they have changed the language in order to be the expansion of space. And then when you ask people what that means, they just kind of babble incoherently until you stop asking.
It's like they eventually will define space as this systematic measurement of distances. And so you're saying the distance is increasing. In other words, they're speeding away. And they're like, no, it's not. And
it's just the expansion of space itself. Okay, so there's something incomprehensible at the center of this that has been added in order to make this work out, because specifically of this thing, which is like, how could they possibly be moving away so fast? How could quasars be producing something at 96% the speed of light?
I was trying to explain this to my students yesterday, actually, and I was just dead stares when I was explaining this. I'm just like, I'm trying to explain the circularity of this argument too, and it's just so hard to make the point. I don't know. It's just lost on people.
Yes, and to me, nothing of these things they make any sense at all. But you see, Hubble.
I have a question about modern day. We've found, not we specifically, but galaxies now have a redshift of like 15, 16.
Yes.
So what is the speed at which they should be moving if this relationship is maintained?
That's a precise point, Anastasia. It's very nice that you brought this to our conversation. Because in Hubble's first paper, it was, as I said, 6 times... the V over C was 6 times 10 to minus 3, which is a very small value. Okay? Then in 1942, he was obtained a V which was 1 over 7 of the velocity of light, which was huge. As I said, the velocity, orbital velocity of the Earth around the Sun is 10 to minus 4, okay? It is 30 kilometers per second. If you compare that with light velocity, is 1 over 10 to the 4, okay? It's a very tiny. But we know that the solar system as a whole is orbiting around the center of the galaxy. All the galaxies, the spiral galaxies, they are spinning. And there is a very curious phenomenon. When you measure the radial velocity of the galaxies around the center, they don't decrease as they should. They reach a plateau, which is called the flat rotation curves of galaxies. And the order of magnitude is like 200 kilometers per second, 250 kilometers per second, any kind of these galaxies. Let us say 300 kilometers per second. If we compare this velocity of the solar system relative to the center of the galaxy, 300 kilometers per second, let's say, to simplify. If you compare that with light velocity is 3 times 10 to 8 meters per second. 300 is 3 times 10 to 5 meters per second. One over the other gives 10 to minus 3. So all velocities of large bodies are 10 to minus 3 or 10 to minus 4 times the velocity of light. But when Hubble himself found in 1942 a velocity of a galaxy which was 10% the velocity of light, he said, come on, that cannot be the case. In 1997, Anastasia, Hubble died in 1953. in 97, the largest redshift measured was around 2.5, which means if you convert that to velocity, which the galaxy would be moving away from us at 90% of the light velocity. In this case, it was not a galaxy. It was in 1970, this record was from a quasar, a quasi-stellar object that is tiny as a star, but emits in radio frequency. So it is called a quasi-stellar object, which they call quasar. So it was a quasar which had the highest redshift. But as Shiloh mentioned, nowadays, I believe, Shiloh, the record is a redshift of 14 nowadays. And it is not for a quasar, it is for a galaxy. And if you convert this redshift, which they call it Z, letter Z, if you convert that into velocity, utilizing Hubble interpretation, that would mean that the galaxy would be moving away from us at 99% of the light velocity, which just, to me, that makes no sense, because the galaxy, it has the same shape as Andromeda. It is spiral galaxies. The chemical elements are the same, and it has a mass of a galaxy, a huge mass. It cannot accelerate to a light velocity. To me, it makes no sense. Moreover, they find these galaxies with these huge modern telescopes. The largest one, which is in space, I forgot its name. The
James Webb
telescope, yes. And they found it in the beginning of the universe. So just like in the first 3 seconds of the universe, they create a galaxy, which takes billions of years to form and billions of years to spin around its axis.
I mean, to be fair, I think it's like 300 million years after the birth of the universe, but
yes,
it's a very short amount of time.
Yes, in 300 million years, you will create a galaxy and it will spin.
I want to say also, there's another issue here, maybe you can comment on it too, which is that this kind of feeds back on itself, because at some distance, you can't use the Cepheids to measure distance. You can't use the supernova. So the only thing you have is redshift. And so redshift is taken as an a priori readout of distance, right? And so if redshift doesn't mean what we think it means, then our distances might be completely broken as well.
Yes, there is a problem, Charles. There is a famous astronomer, Houghton Arp, A-R-P. I met him in some conference abroad in the past. He is already dead, unfortunately. But he was an American who did work in Mount Palomar, very famous observatory, and he was specialist in quasars. And at that time, in the 1960s, 70s, when they discovered these quasars, as I said, they are just like a star, but they don't emit essentially invisible light. They emit in radio frequency. But they have a huge redshift at that time, 1 or 2 or so, which was much higher than the redshifts of the galaxies. Oh, they said, then they must be at the end of the universe. If redshift is an indicator of distance, as you said, Shiloh. But then, to see that quasar that you are measuring with your telescope, if it is in the end, at the end of the universe, it must have a huge amount of energy which no physical mechanism explains. To be
Enter
so
black
far
holes.
away and to shine that we can detect with the telescope at Palomar, as Arp found. And then Arp began to discover many interesting phenomena. Normally, these quasars, they were found close to active galaxies, which have anomalous shape, which have a very peculiar kind of light which they emit. They are, and normally, if you have a galaxy here, he found a galaxy in the top and in the bottom, around the axis of rotation of the galaxy. And then people said, but the redshift of the galaxy in the middle was much smaller than the redshift of the quasars, which were in both sides. Then people said, and the quasar should be at the end of the universe, and the galaxy close to us. And people said, no, you are just looking, and they look like they are close, but they are very far away. But he began to find many examples of quasars which were associated with nearby galaxies. Then he even published a book, an atlas of anomalous redshifts of these galaxies. And then he made a proposal that there are intrinsic origins of redshifts in some of these objects, and that these quasars that we see on both sides of an active galaxy nuclei, they had been ejected by this galaxy, and normally in both directions. So you find quasars in both sides of the galaxies, but also they have much higher redshift. It's because they are like younger galaxies. They will evolve into mature galaxies in the future. And so as time goes by and these quasars are transforming into a galaxy, its intrinsic redshift decreases. So to this astronomer, ARP, there are situations in which redshift is not associated with distance to us.
And this is also very unpopular because the commonplace knowledge with the Big Bang cosmology is that the galaxy is only formed once, essentially. That there's only been enough time to do this once. And so this idea that they could be forming at any time, that quasars could represent a stage in their evolution was outlawed from the beginning, essentially. I also wanted to mention ARP was one of Hubble's students, from what I understand. He was a graduate student under Hubble, which is pretty remarkable.
Maybe. And you see, ARP began to publish. He was not a theoretician. He was an observational astronomer. And he was the major specialist in quasars. But when he did begin to publish these ideas that maybe the quasars, they are associated with nearby galaxies, also they have a huge redshift. So they are physical, and even sometimes he even found physical connections. Mm-hmm. Sometimes the galaxy has a luminous trail which goes directly to the quasar at one side or to the other side. And he published books and papers on these. And then people from the establishment began to be upset because he was questioning the Big Bang. But he said, this is what I find with my telescope. And then one day he received a letter, I believe from the head of the Palomar Observatory. He was prohibited to utilize time of the telescope to make research on quasars.
No.
So it was just like Galileo 200 years, 300 years before. It happened with Houghton ARP.
Did they also burn him at the stake, or?
It is analogous. So he was rejected in many conferences. His papers were rejected in many journals. And sometimes he did need to publish in journals which were not so important because the main journals rejected some of his papers. But he was very outspoken. And happily, in Germany, they could find him a place after he could no longer utilize the telescope in Palomar, so he could continue some of his work in Germany until he died there. And he was American, not German, but
So the mainstream conception at the time is that these are really far away objects, these quasars, and that they're super luminous, so they have to have some energetic source that's beyond conception. And at some point, the black hole, the supermassive black hole, gets at, that becomes a popular idea on the back of the relativism. And
but you see,
hold on, I have a question.
Yes.
A quasar, you said earlier, is a quasi-stellar object.
Yes.
Are they thought to be like size similar to stars?
No. They are like stars in the sky.
I see.
But they should, as they are too far away, they should be huge. And so, but there is no physics to explain them, okay? But nowadays we have the same problem, because now the record redshift is no longer with these quasars, which might be these strange objects, but with galaxies. With this James Webb telescope, we find galaxies with a redshift of 10, which means it is in the far end of the universe, but we can see that.
And so what were you saying about the relationship of quasars to black holes?
Well, I'm just saying that we didn't totally steel man the mainstream explanation for quasars, but they believe that it's a particular kind of active galactic nuclei, this AGN. So it's like there's a big supermassive black hole at the center of these galaxies that's doing some crazy magic to result in these massive energetic outbursts, which we associate with quasars.
Are they thought to be on the size scale of galaxies now?
Their signal like overwhelms the galaxy even. They're so bright.
So they're just these unbelievably either bright or unbelievably large objects. Are they still
they're
thought
supposed to be very small? Like when they do the light curve studies, they find, I think, that they fit within a few light days or like a light month or something. They're very small concentration up. But this leads to the black hole theory, essentially. But again, like all of these concepts like distance, brightness, redshift, they're all intertwined and they might point to very different phenomena. Yes. So when you conflate all of them, you end up having to invent these unimaginable situations where physics breaks down, aka the supermassive black hole, to explain what's happening. Because you're trying to explain something that's probably far more energetic than it actually is. And, the distance estimate is probably off by orders of magnitude as well. So you get confused very quickly.
Okay, and so how do these two threads, which still seems like there's plenty of people that are going around that are suggesting that the redshift measurements can't possibly be interpreted as either the expansion of space or the motion of distant objects away from us. They're saying that there must be a different explanation. There's all these people that are going around saying that there's a different explanation for the CMB. So bring us home to this question of how is it that in 1964, when Penzias and Wilson and Dickey publish, everybody's like, great, Big Bang, we're done. Like, what happens? Because there's all of this debate.
Because it happened already before, as I said. When Hubble published his first paper with his law, 1929, he connected, unfortunately, his law with this de Sitter universe, this de Sitter effect of general relativity. You see, Hubble met de Sitter in Holland, in Leiden, before that, 1928, I guess. And so that virus went into Hubble's mind. So when he found this relation, he connected that with this general relativity and so on. But when
Hubble was like a demigod. Like he was such an important person that because he had been at least temporarily won over to the expansionist idea, there was no way going back. It's kind of like how Einstein gets in trouble for dismissing the ether, but then he's like, no, that's not totally what I meant, but then it's too late because the cat's out of the bag kind of thing.
And
yes, you see.
How was Hubble convinced to the expansion side of things? Did we cover that?
Well, I think he's still trying to explain to himself how in the world something could possibly be moving at near light speeds, some fraction of light speed. He doesn't know how to do it, right? So the Doppler explanation boggles the mind. If you introduce I don't know how you're won over by this argument. It bothered me when I was 11, but if you're won over that the expansion of space is a sufficient workaround, then you're won over. Then you're drinking the Kool-Aid.
But you see, Hubble tried to propose tests of this expansion. He's a fascinating guy. He did publish papers with a famous physicist from Caltech, Richard Tolman, which is called the Tolman effect and so on. And they did propose some tests to see if the redshift was due to Doppler or to another mechanism. He could, in his tests, when he was alive, the tests did favor slightly the universe without expansion. And he did publish that. And but even nowadays, there is so much discussion. And as Shiloh said, everything is interconnected. Luminosity, frequency, motion, expansion of space, and so on, that you can get any result you wish for any of these tests. So the situation is a great mess nowadays. But during Hubble's life, he did publish these tests with Richard Tolman, and they did conclude from his measurements that they were more compatible with a universe without expansion than with the Big Bang. And I believe that, I already heard that Hubble didn't get the Nobel Prize because he did begin to question Einstein's general theory of relativity. If he didn't begin to question Einstein's relativity, maybe, we don't know, no one knows, but maybe he would got the Nobel Prize for Hubble's law. But as he himself began to question the standard interpretation, he began to be put aside. Hubble himself. And he died in 1953. Never won the Nobel Prize, but until the end of his life, in all of his publications, with the exception of the first, in which he got the law and mentioned this de Sitter effect, I did publish a paper in 2009 based on a conference which happened in Seattle, USA. That was the second Crisis in Cosmology conference. I did publish a paper with two colleagues of mine, Marcos Neves, who I already mentioned, and Domingos Soares from Federal University of here in Brazil. And this paper is called Hubble's Cosmology, from a finite expanding universe to a static, endless universe. That is a universe without Big Bang. So Hubble himself, in his first paper, he assumed expansion, the Sitter effect. From all other papers and books which he did publish, we did quote many passages, the words of Hubble, in papers and in his books, showing that he was, after the first, always in favor of an infinite universe in space, in time, and without Big Bang, without expansion. However, he could not find a mechanism to explain the cosmological redshift. I will just quote here the last sentence of his book from 1937, and which is called, I forget the name, but the sentence, the last sentence of this book is the following, words by Hubble. We seem to face, as once before in the day of Copernicus a choice between a strangely small finite universe and a universe indefinitely large plus a new principle of nature. And from this sentence, he said, strangely small finite universe. He didn't like it. He did prefer a universe indefinitely large. In some of his papers and books, he mentioned infinite universe, existing for an infinite amount of time, and a new principle of nature. What was this new principle of nature? Something which did cause the redshift of the galaxy to reach us, which was not Doppler.
Can we talk about the search for a theory of this tired light, like why it has been defeated so many times? Because maybe Nastya, you can mention what you were looking into some of the standard criticisms during the break.
Well, it was Zwicky who proposed the idea of tired light and who was, I think, basically laughed out of the room because his idea was that photons from distant galaxies were colliding with things along the way and reddening as a result of those collisions. And everybody was like, well, if they're colliding, they're scattering. And so you should see everything far away be blurry. And it's not blurry, ergo it can't be this sort of collisional model.
This is one problem, Anastasia, very important one, this scattering. So the images of the distant object should be blurred, but we see them very sharp with this James Webb telescope and so on. And but you are right. One of the first people to propose a mechanism different from Doppler was Fritz Zwicky. Zwicky. And this Zwicky, he proposed that in 1929. He was, I believe, even a colleague of Hubble or so. And so Hubble, and he proposed maybe due to this gravitational redshift as well. And so, but there have been different proposals. As I said, this Nernst mentioned maybe dust, this Finland-Freundlich, maybe photon-photon interaction. And it was this idea of photon-photon interaction which made Max Born make the prediction that if it is photon-photon, then the cosmological redshift should be connected with radio astronomy before Penzias and Wilson. Hubble himself, he has some sentences in which he said, either it is Doppler or light is interacting with its journey from a distant galaxy until it reaches us with this intergalactic media. And he even mentions that intergalactic media cannot be empty. There must be dust, matter, radiation, and so on. But the point is, for instance, if we assume Compton effect, as I said, the redshift due to Compton should depend on frequency. So it should be spectrum dependent, the Z. And this is not measured. The redshift seems to be the same, at least until now, for all frequencies. So Doppler has this property. So that is a point in favor of Doppler. But for this reason, Hubble looked for another mechanism, but he couldn't find. But he always finished his papers and his books with this quotation that either it is Doppler or the universe is infinite in space and time, but we need another mechanism, which we still didn't find.
Has anybody proposed something other than scattering or something like? Is there a solution that's obvious that doesn't involve the chromatic aberration and so forth that we would?
There are many proposals. There are many people even which propose a Compton effect, and they make some. They explain why it will be not dependent on frequency and so on, and why the image will not be blurred and so on. Maybe they are right. I don't know.
Mm-hmm.
I myself, I don't have
do you know the work of Carver Mead and John Kramer with the transactional interpretation of quantum mechanics?
I just heard of it, but never did study it.
It's really fascinating. I think it was in 1936, G.N. Lewis, the chemist, just proposed very briefly in this paper that he didn't believe in the idea that light was just this little thing that was shot off of an atom. He believed that there was always two atoms involved in a transaction. And so, through many conversations with Carver over the years, and we talked to John Kramer too, who developed this idea, they essentially see that all light is the result of these intense relay systems among networks of atoms that are affecting one another. And so even when you have a situation like neutral hydrogen, where the light, the way we're taught in the textbook that the light doesn't interact with neutral hydrogen, the transactional interpretation would say that it's less lossy of an interaction. In other words, it's approaching the limit of being a lossless transaction, but still the light is being relayed across those atoms in the field of view. In other words, like the light coming between my eyes and the screen right now is still being relayed across all of the gas atoms in the room. It's just not that lossy. And so if you really dig into the transactional interpretation, you might be able to approach a solution where over vast cosmic distances, these interactions do add up to a loss that's appreciable.
And it's actually interesting because it is in some way in line with what Hubble is saying about some new principle of physics, because it's not a scattering collision the way that you would envision for Zwicky's tired light.
Right.
It's something that is almost, and it's something that's it
requires a reconception of what light is, fundamentally.
It requires a reconception of what light is, but I also think about the event itself, right? That the photon interacts with this atom, and there's a lack of resistivity to the relay. Like, I can imagine in my mind as this, because the atom, it has some kind of inherent motion to it, right? And so a photon comes, it perturbs that motion, but it's so harmonic that it just is able to give it off to the next atom in line towards us.
Yes. And this brings to mind, yes, please, go ahead.
I'm also thinking about the early theories about the nature of light, where they treated it as being like a radial phenomenon. And so if you read like Euclid, he explains why you can't find a needle on the ground the first time that you look, is that the needle is between these rays that are emanating from your eyes, and so you move, and then all of a sudden the ray falls and you can see it. And I feel like that radial emanation from very distant galaxies also kind of solves the scattering problem, because how much of the light that comes from the radial galaxy, from the galaxy at a great distance, is actually in line with this tiny object of Earth at this great distance. Like anything that scatters away just would scatter away from the Earth, right?
Well, I mean, that's the origin of the inverse square law, ultimately.
Sure,
these radiations dissipate across
This
space.
reminds me, Anastasia and Shiloh, a guy I met many years ago in some conference. He is already dead, unfortunately, as well. His name was Roberto Monti, an Italian. And he proposed that the redshift, cosmological redshift, was connected with the resistivity of the intergalactic medium. Because as you said, Anastasia, and we are talking about a signal propagating around a wire. If there is no resistivity, it propagates at light velocity. But if the wire has some resistivity, if the medium where the electromagnetic wave propagates has some resistivity, there will be some exponential decay in the signal. which we see waves might be analogous to a redshift. So the possibilities, they are many. But even if we don't find the mechanism, one day we will find, I have no doubt of it. But it may take 1 year, 10 years, 1 century, I don't know. But even if we don't find, I would prefer that we keep this Hubble open-mindedness, saying that either it is Doppler or it is a new principle of nature. But even if we don't know this new principle of nature, we can make tests. If the galaxy is stationary, there will be not only the redshift, but other properties. If it is moving away, there will be not only Doppler, but other consequences as well. And so this was the frame of mind of Hubble, of an observational astronomer, that we can test these different explanations, even without knowing a mechanism. And there may be many mechanisms at once. For instance, we can have one mechanism which gives this redshift as a function of the distance of Hubble's law. But we also have this, as I said, this Hawthorne arc, which found quasars, which are at the same distance to us as the galaxy in the middle, but has a much higher redshift. So it is something around the quasar, like a plasma, when it is moving through these very high density plasma with radiation field, which causes a very huge redshift for the quasar and not for the galaxy nearby. And so many mechanisms should be at work at once, because we have many things which create which produce redshift, as I said, Doppler, gravitational, fluorescence, Compton, dust, any kind of interaction. So all of them can be happening at the same time. No problems. We don't need to have only one mechanism. As I said, I don't doubt the Doppler effect. It exists, it has been measured, but I don't think it explains the cosmological redshift. I don't think it explains the redshift of quasars. In this case, we have other which are more relevant, more important. And so I like very much this paper by Finland Freundlich, 1954, because with this formula that the redshift is not only proportional to the distance, but to the force power of the temperature where the light is moving, he could explain so many different observed redshifts in the sun, in A stars, O stars, white dwarfs, and even the cosmological redshift. So he seems to be got something very important, which should be better known and explored, advanced. So for this reason, it was very nice that you invite me. Maybe people who will watch us will have an inkling, that an insight, and that may lead to the 5th Nobel Prize for someone who worked with an infinite universe without expansion and without Big Bang, which will then turn the paradigm once more.
Yeah, if you're listening to this, you should consider coming out to Portugal and come and talk to us. Come talk to André.
Yes.
We will be discussing these matters. And there's a number of really big minds that are going to show up and talk about these matters. So I think it's almost better. I actually have a lot more questions about this, but we're going to talk about it a lot this summer. So I think we should put a pin in it and save it for June. And
who is watching us, yes, should go to Portugal and
come on out.
Meet us there personally. Then we can discuss in the coffee, during lunch, during dinner, in the beach, and so on. And so that will be great.
I think it's going to be really wonderful. And the spirit of inquiry is what I hope will really be reborn at this conference, where it doesn't have to be one answer. The universe is complicated. There's many things at play, and I think that it's far more fruitful to take the approach of wonder than it is to take the approach of, no, we've figured everything out. We have given the prizes. There is nothing remaining.
And you see, you, Anastasia, and you, Shiloh, you see, Houghton Art was prohibited to present his work in some conferences.
That's crazy.
He had abstract rejected, a great astronomer. And you are doing the opposite. You are inviting people to question the mainstream, to question the paradigm, dominant paradigm. That is great of both of you. So you are doing a great job.
Yeah, and by the way, we're not doing that because we're rebels. Like, we're doing that because there's these huge anomalies that require reconsideration. It's not really heresy or anything. I mean, I think that people who are censoring perspectives are never on the good guy side in the rear view mirror when we look at history. So, you know, the spirit of open inquiry is the heart of science. That's the beautiful Royal Society from back in the 18th, 19th century. That's what we want to revitalize. We want to actually have an open conversation about the anomalies that doesn't just point at supernatural explanations and call it a day. So I don't think we're doing anything particularly rebellious. We're just, you know, trying to open up the book on some of these problems.
But you are giving space to some people who don't have the opportunity to present their work, their observations and so on, either in conference or in papers or in books. And you are giving these with your podcast, invite so many different people with so many different ideas from the established ideas. This is so important.
And we're going to have some establishment people there too, so they can make sure that we get all the facts straight. You know, there's not like we're going to just be presenting one side of the story. And I think that's really important too, is to have somebody there to defend this mainstream perspective at the same time. So,
or to at least advocate for it in the sense of, well, hey, hold on a second. These are the anchor points.
Even the murderer gets a defense lawyer at the trial.
I was going to say, André, we should hire you as our hype man for the conference. You do a much better job of promoting this than we do. You've managed to get it into the conversation at least 4 or 5 times.
That is excellent what you are doing. It's just a wonderful job. I'm very happy that up to now we only met online, but in June we will finally meet in person. So I think that will be great opportunity.
I'm really excited for it.
Yeah.
Well, thank you so much again for coming by. And yeah, let's just keep the conversation going in June. And we'll get this out to the world. I hope people listening will come out and discuss with us, and we can hopefully get closer to understanding what's going on in this universe of ours.
Agreed.
Thank you very much. And for those of you who wish, all the things that I mentioned here, they are available in papers or in books in my homepage that you can just open and download the papers, the books, and so on. Thank you very much, Iros. Thank you very much, Anastasia. And see you in Portugal.
Excellent.
Right,
Thank you so much, André.
Have a great rest of your day.
Bye, everybody.
Bye, folks.